Let's see.
Okay. Yeah. Seems still to work, even with limited experience. Okay, so it's a pleasure to introduce Andrej. I have to say, I think he doesn't really need a lot of introduction. But yeah, he is the senior director of AI at Tesla, and he basically supervises and leads the team responsible for all the neural networks in the autopilot. With this, it's a pleasure to have you here, and I'm really looking forward to your talk.
Yeah, great. Thank you for the introduction. And I'm very happy that I was able to display some impressive zero-shot learning on Zoom. Okay. Yeah, so I'm very excited to be here. Thank you for the introduction. I would like to talk a bit more about what Tesla has been up to over the last few months. So first to start, I guess we are here at the CVPR workshop on autonomous driving. So I think I'm preaching to the choir a little bit, but I'd like to start with some slides on like why we're doing all of this. And I think, unfortunately, we're kind of like in a bad shape when it comes to transportation in society. And basically the issue is that we have these metallic objects traveling incredibly quickly and with very high kinetic energy. And we are putting meat in the control loop into the system. And so this is quite undesirable. And really fundamentally what it comes down to is people are not very good at driving. They get into a lot of trouble and accidents. They don't want to drive. And also, in terms of economics, we are involving people in transportation. And of course, we'd like to automate transportation and really reap the benefits of that automation in society. So we all, I think, are on the same page that it should be possible to replace the meat computer with a silicon computer and get a lot of benefits out of it in terms of safety and convenience and economics. So in particular, silicon computers have significantly lower latencies. They have 360-degree situational awareness. They are fully attentive and never check their Instagram, and alleviate all of the issues that I presented. And so I think this is not super shocking, and a lot of people have been kind of really looking forward to this kind of a feature. This is a frame from iRobot, fully attentive and never check their Instagram, and alleviate all of the issues that I presented. And so I think this is not super shocking, and a lot of people have been kind of really looking forward to this kind of a feature. This is a frame from iRobot, a really good movie if you haven't seen it. And here, Will Smith is about to drive a car manually. And this other person here is shocked that this is going to happen. This is ridiculous. Like, why would you actually have a human driving cars? And so I think this is not very far from truth. And this movie is taking place in 2035. So I think by then, I actually think this is a pretty prescient prediction. So what I think is kind of unique about Tesla and in our approach to autonomy is that we take a very incremental approach towards this problem. So in particular, we already have customers with the Autopilot package, and we have millions of cars, and the Autopilot software is always running and providing active safety features, and of course, the Autopilot functionality. So we provide additional safety and convenience to our customers today, and also the team is working on full self-driving ability. So I would briefly like to very quickly speak to the value today that we provide, just to give you some examples of what the team is up to and what we're sort of doing today. So here's an automatic emergency braking scenario. So the driver here is proceeding through an intersection, and you can see trouble coming here. So the person kind of crept up from here, and the car sees the pedestrian, object detection kicks in, and we slam on the brakes, and we avert a collision. Here's an example of a traffic control warning. So this person is probably not paying attention, potentially on the phone, is not braking for the traffic lights ahead, but we see that these are relevant traffic lights. They are red, and we beep, and the person immediately starts slowing and probably does not actually enter the intersection. These are examples from pedal misapplication mitigation, PMM. Here, a person is unparking from their driving spot, and they are trying to turn, and then they mess up, and they accidentally floor it. So they floor it right there, and the system kicks in. It sees pedestrians ahead of us, and it slams on the brakes and averts what would be a very gnarly situation in this case. Here's another last scenario I can show briefly. So this person is trying to park, and they turn to the right here, and they intend to press the brake, but they actually floor it. And the system, again, sees that there's no driving path forward and actually slams. Here's another last scenario I can show briefly. So this person is trying to park, and they turn to the right here, and they intend to press the brake, but they actually floor it. And the system, again, sees that there's no driving path forward and actually slams on the brakes and averts. In this case, this person is not going to be swimming in this river imminently. So these are some examples of the value that we are providing today in this incremental autonomy fashion. But of course, the team is actually... Sorry about that. The team is working primarily on the FSD functionality, which is our full self-driving suite. So here we have we have the FSD beta product, and it's in the hands of about 2,000 customers. And this is an example from one of the customers driving around San Francisco. And these people are posting videos on YouTube, so you can check out a lot of videos. But what we're showing here on the instrument cluster is we're showing all of our predictions. So you're seeing some road edges, some lines, some objects, and the car, of course, is navigating around autonomously here in San Francisco environment. Now, we, of course, drive this extensively as engineers. So it's actually fairly routine for us to have zero intervention drives, I would say, in like sparsely populated areas like Palo Alto and so on. I would say we definitely struggle a lot more in very adversarial environments like San Francisco. A lot of people working in autonomy, of course, know all about that as well. So this drive ends up being a fairly long drive, and it's zero interventions in this case. Now, one thing I like to point out always whenever I show the video of Tesla driving around autonomously in these city environments is you've seen this before, and you've seen it for a decade or more. So here's a Waymo taking a left at an intersection. And this is actually a pretty old video, I believe. And so you've been seeing stuff like this for a very long time. So what is the big deal? Why is this impressive? And so on. And I think the important thing to realize, and that I like to always stress, is that even though these two scenarios look the same, so there's a car taking a left at an intersection, under the hood, and in terms of the scalability of the system, things are incredibly different. So in particular, a lot of the competing approaches in the industry take this LiDAR plus HD map approach. And so the idea is that you take an expensive sensor, a LiDAR, on the top of the car, and it basically gives you range finding around the vehicle in 360 and gives you a point cloud. And what you have to do is you have to pre-map the environment so in particular, a lot of the competing approaches in the industry take this LiDAR plus HD map approach. And so the idea is that you take an expensive sensor, a LiDAR, on the top of the car, and it basically gives you range finding around the vehicle in 360 and gives you a point cloud. And what you have to do is you have to pre-map the environment with the LiDAR sensor, and you have to create a high definition map. And then you have to insert all of the lanes and how they connect and all the traffic lights and where they are. And you basically have to create a high definition map. And then at test time, you are simply localizing to that map to drive around. And so the approach we take is vision-based primarily. So everything that happens for the first time there in the car based on the videos from the 8 cameras that surround the car. And so we come to an intersection for the very first time, and we have to figure out where are the lanes, how do they connect, where are the traffic lights, which ones are relevant, what traffic lights control what lanes. Everything is happening at that time on that car, and we don't have too much high definition sort of information at all. And this is actually a significantly more scalable approach, because if our product is on a scale of millions of customers on Earth, and so it's actually quite unscalable to actually collect, build, and maintain these high definition LiDAR maps. It would be incredibly expensive to keep this infrastructure up to date. And so we take the vision-based approach, which of course is much more difficult because you actually have to get neural networks that function incredibly well based on the videos. But once you actually get that to work, it's a general vision system and can in principle be deployed anywhere on Earth. So that's really the problem that we are solving. Now, in terms of the cartoon diagram of a typical sensing suite of an autonomous vehicle, these are kind of like the typical sensors you would see. And as I mentioned, we do not use high definition maps and we do not use LiDAR. We only use video cameras. And in fact, the vision system that we have been building over the last few years has been getting so incredibly good that it's kind of leaving a lot of the other sensors in the dust. And so actually, the cameras are doing most of the heavy lifting in terms of the perception that you've seen in the car. And actually, it's gotten to the point that we are able to start removing some of the other sensors because they are just becoming these crutches that you start to not really need at all. So actually 3 weeks ago, we started to ship cars that have no radar at all. So we've deleted the radar and we are really need at all. So actually 3 weeks ago, we started to ship cars that have no radar at all. So we've deleted the radar and we are driving on vision alone in these cars. And the reason we are doing this, I think, is well expressed by Elon in his tweet. He's saying, when radar and vision disagree, which one do you believe? Vision has much more precision, so better to double down on vision than do sensor fusion. And what he's referring to is basically like vision is getting to the point where the sensor is like 100x better than, say, radar. Then if you have a sensor that is dominating the other sensor and is so much better, then the other sensor is actually starting to like really contribute. It's actually holding you back, and it's really starting to contribute noise to the former system. And so we are really doubling down on the vision-only approach. And actually in this talk, what I would like to primarily talk about is how we have achieved vision-only control without radar and how we have released this quite successfully so far to the fleet and what it has sort of taken for us to do that. So here I wanted to show a video basically showing what the input to the system is. So we have 8 cameras surround, and these are fairly high definition cameras, and we have 36 frames a second. And you can see that basically you can actually understand a lot about this environment from this input. It's extremely information rich. You're getting a huge amount of constraints, 8 million bits roughly of constraints per second on the state of the surroundings. And so it's incredibly information rich compared to any other sensor you may want to have in a car. And so this is the one that we're doubling down on because this is ultimately where all the difficult sort of scene interpretation challenges lie. So we prefer to just focus all of our infrastructure and development on this. And we're not wasting people working on the radar stack and the sensor fusion stack. We only have one team, the vision team. Now, typically when we talk about vision, the reason people are squeamish about using vision is, and the sort of challenge that almost always is pointed out, is people are not certain if neural networks are able to do range finding or depth estimation of these objects. So obviously humans drive around with vision. So obviously our neural net is able to process visual input to understand the depth and velocity of all the objects around us. But the big question is, can our synthetic neural networks also do the same? And I think the answer to us internally over the last few months that we've worked on this is an unequivocal yes. And I'd like to sort of talk about that. So in particular, the radar API, or like what the radar really gives you, is pointed out, is people are not certain if neural networks are able to do range finding or depth estimation of these objects. So obviously humans drive around with vision. So obviously our neural net is able to process visual input to understand the depth and velocity of all the objects around us. But the big question is, can our synthetic neural networks also do the same? And I think the answer to us internally over the last few months that we've worked on this is an unequivocal yes. And I'd like to sort of talk about that. So in particular, the radar API, or like what the radar really gives you, is it gives you a quite accurate depth and velocity measurement. It's a pretty direct measurement of the car ahead of you in very nominal situations. So here I'm showing a random image on the left, and you are seeing the depth, velocity, and acceleration reported by the radar stack for this car. And you can see that it's a bit wiggly on the velocity, so this is some kind of a stop and go scenario. Now, when radar has a good lock on the car in front of you, it's given incredibly good depth and velocity. But the problem with radar is, like, once in a while, at random, it will give you a dumb measurement and you will not know when that is. And so it's incredibly hard to fuse with vision in our experience. So it might suddenly see a spurious stationary object because of a manhole or because of a bridge, or crossing objects are not very well tracked, or oncoming objects are not very well tracked. And it ends up contributing noise. I'll go into more detail in a bit. But for our purposes, what we want to do right now is we want to match the quality of these predictions using vision alone. So the question is, how can you get a neural net to predict depth, velocity, acceleration directly and do it with a very high fidelity, matching that of radar? So the approach we're going to take, of course, is we're going to treat this as a supervised learning problem, and we need a massive data set of depth, velocity, acceleration on a lot of cars, and we're going to train a large enough neural network and do a very good job at that. That's the standard vanilla approach, and that actually works really well if you do it properly. So here's what it took. So the first component that you need is an incredibly good data set. So, and when I talk about a good data set, I believe it has to have 3 properties that are critical. It has to be large in millions of examples. It needs to be clean. So in this case, we have to have a very clean source of depth, velocity, and acceleration for all these cars. And it must be diverse. So we're not just talking about a single, driving clip of going forward on a highway. We really have to get into the edge cases and mine all the difficult scenarios. And I'm going to show you some examples. And when you have, if you do it properly. So here's what it took. So the first component that you need is an incredibly good data set. So, and when I talk about a good data set, I believe it has to have 3 properties that are critical. It has to be large in millions of examples. It needs to be clean. So in this case, we have to have a very clean source of depth, velocity, and acceleration for all these cars. And it must be diverse. So we're not just talking about a single, driving clip of going forward on a highway. We really have to get into the edge cases and mine all the difficult scenarios. And I'm going to show you some examples. And when you have a large, clean, diverse data set, and you train a large enough neural network on it, what I've seen in practice is, in the words of Ilya Sutskever, success is guaranteed. And so let me show you some examples of that. So first of all, how are we going to achieve this data set? So of course, we need to collect training data. The typical approach might be to use humans to annotate cars around us in 3 dimensions. What we found actually works really well is an auto-labeling approach. So it's not pure humans, just like annotating cars. It's an offline tracker, as we call it, and it's an auto-labeling process for collecting data at the scale that is necessary. So we need, again, millions of hard examples. So this is where the scale comes from, is that it's not labeled purely by humans, although humans are involved, it's labeled automatically. So here's an example of some automatic labels we were able to derive for cars on the highway. And the way you do this is, because you are offline and you are trying to just annotate a clip, you have a large number of benefits that you don't typically have if you're at test time under strict latency requirements in the car. So you can take your time to fully figure out exactly all the objects and where they are. You can use neural networks that are extremely heavy, that are not deployable for various reasons. You can use benefit of hindsight because you know the future, not just the past. You can use all kinds of expensive offline optimization and tracking techniques. You can use extra sensors. In this case, for example, actually radar was one of the sensors that we used for the auto labeling. But there's actually a massive difference between using radar at test time and using it in the offline tracker. And that is that at test time, a radar can just report a stationary track immediately in front of you, and you have 20 milliseconds to decide if you're going to brake or not. If you're offline, you have the benefit of hindsight. And so you can do a much better job of calmly fusing if you really want to. You can do a much better job of calmly fusing if you really want to. And so there is a massive difference there. And in addition, you can, of course, involve humans, and they can do cleaning, verification, editing, and so on. And so we basically found that this was a massive lever to allow us to reach the scale and the labeling quality. And then to get the diversity, that was also a massive fight. So here's some examples of really tricky scenarios. So here, there's some, I don't actually know exactly what this is, but basically this car drops a bunch of debris on us, and we maintain a consistent track for the label. And of course, if you have millions of labels like this, the neural net, if it's a powerful enough neural net, will actually end up learning to persist these tracks in these kinds of scenarios. Here's another example. There's a car in front of us, and I actually am not 100% sure what happens in this case, but as you'll see, there's some kind of a dust cloud that develops here and briefly occludes the car. But in the auto-labeling tool, we are able to persist this track because we saw it before and we saw it after, so we can actually stitch it up and use it as a training set for the neural net. Here's one more example of an adversarial scenario from heavy snow. Again, we can auto-label this fine and create a large collection of examples. Now, as we were working on this over a duration of, I want to say, of roughly 4 months of really just focusing a lot of the team on this problem of achieving really good depth, velocity, and acceleration, we've ended up developing 221 triggers manually that we were using to source data from our customer fleet. And this is just an example, some examples of the 221 triggers that were used to collect all of these diverse scenarios. So for example, we have shadow mode, where we deploy a neural network that is pretty good at predicting depth and velocity. And what we do is we run it silently in the cars of our customers, but it's not actually connected to control. What's driving is the legacy stack. But we're basically running the new measurements of depth and velocity, and we're, for example, looking at whether or not they agree or disagree with the legacy stack or with the radar. We're looking for other sources of jank, like, for example, if there's bounding box jitter, detection jitter, the main and the narrow camera disagree. We predict that there's a harshly decelerating object, but the person seems to not mind. All kinds of disagreements between different neural network signals that we're using to source data from our customer fleet. And this is just an example, some examples of the 221 triggers that were used to collect all of these diverse scenarios. So for example, we have shadow mode, where we deploy a neural network that is pretty good at predicting depth and velocity. And what we do is we run it silently in the cars of our customers, but it's not actually connected to control. What's driving is the legacy stack. But we're basically running the new measurements of depth and velocity, and we're, for example, looking at whether or not they agree or disagree with the legacy stack or with the radar. We're looking for other sources of jank, like, for example, if there's bounding box jitter, detection jitter, the main and the narrow camera disagree. We predict that there's a harshly decelerating object, but the person seems to not mind. All kinds of disagreements between different neural network signals. And there's a long list here. It took us a while to actually perfect these triggers, and all of them are iteration, and you're looking at what's coming back, you're tuning your trigger, and you're sourcing data from all these scenarios. So basically over the last 4 months, we've done quite extensive data engine, and we've ended up doing 7 shadow modes and 7 loops around this data engine here, where on the top right is where you begin. You have some seed data set, You train your neural network on your data set, and you deploy the neural network in the customer cars in shadow mode. And the network is silently making predictions. And then you have to have some mechanisms for sourcing inaccuracies of the neural net. So you're just looking at its predictions. And then you're using one of these triggers, like I described. You're getting these scenarios where the network is probably misbehaving. Some of those clips end up going to unit tests to make sure that we, even if we're failing right now, we make sure we pass later. And in addition, those examples are being auto-labeled and incorporated into a training set. And then as a asynchronous process, we're also always data cleaning the current training set. And so we spin this loop over and over again until the network basically becomes incredibly good. So in total, we've done 7 rounds of shadow mode for this release. We've accumulated 1 million extremely hard, diverse clips. And these are videos. So these are, you should roughly think about, say, 10-second clips, 36 FPS, something like that. In total, we have about 6 billion objects labeled cleanly for depth and velocity. And this takes up roughly 1.5 petabytes of. We have about 6 billion objects labeled cleanly for depth and velocity. And this takes up roughly 1.5 petabytes of storage. So that gives us a really good data set. Of course, that by itself does not suffice. So we have an incredibly good AI team that is designing the neural network architecture. There's basically the layout of the synthetic visual cortex in order to efficiently process this information. So our architecture roughly looks like this. We have these images coming from multiple cameras on the top. All of them are processed by an image extractor, like a backbone, like think ResNet kind of style. Then there's a multicam fusion that fuses the information from all the 8 views. And this is a kind of a transformer that we use to fuse this information. And then we fuse information first across all the cameras and then across all of time. And that is also done either by a transformer, by a recurrent neural network, or just by 3-dimensional convolutions. We've experimented with a lot of kind of fusion strategies here to get this to work really well. And then what we have afterwards, after the fusion is done, is we have this branching structure that doesn't just consist of heads, but actually we've expanded this over the last year or so, where you now have heads that branch into trunks that branch into terminals. So there's a lot of branching structure. And the reason you want this branching structure is because there's a huge amount of outputs that you're interested in, and you can't afford to have a single neural network for every one of the individual outputs. You have to, of course, amortize the forward pass for efficient inference at this time. And so there's a lot of feature sharing here. The other nice benefit of the branching structure is that it decouples at the terminals, it decouples all these signals. So if I'm someone working on velocity for a particular object type or something like that, I have a small piece of neural network that I can actually fine tune without touching any of the other signals. And so I can work in isolation to some extent and actually get something to work pretty well. And then once in a while, so basically the iteration scheme is that a lot of people are fine tuning, and once in a while we do an uprev of all of the backbone end to end. And so it's a very interesting sort of mechanism because we have a team of roughly 20 people who are, I would say, training neural networks full time, and they're all cooperating on the single neural net. And so what is the workflow by which you do that is pretty fascinating and continues to be a challenge to actually design efficiently. So we have a neural network architecture, we have a data set. Now training these neural networks. So we have a neural network architecture, we have a data set. Now training these neural networks, like I mentioned, this is a 1.5 petabyte data set, requires a huge amount of compute. So I wanted to briefly give a plug to this insane supercomputer that we are building and using now. For us, computer vision is the bread and butter of what we do and what enables the autopilot. And for that to work really well, you need a massive data set. We get that from the fleet, but you also need to train massive neural nets and experiment a lot. So we've invested a lot into the compute. In this case, we have here a data set. We have a cluster that we're just building that is 720 nodes of 8x A100s of the 80 gigabyte version. So this is a massive supercomputer. I actually believe that in terms of flops, this is roughly number 5 supercomputer in the world. So this is actually a fairly significant computer here. We have 10 petabytes of hot tier NVMe storage, and it's also an incredibly fast storage. So I believe 1.6 terabytes per second. This is one of the world's fastest file systems. And we have also a very efficient fabric that connects all of this. Because of course, if you're doing distributed training across your nodes, you need your gradients to be synchronized very efficiently. And of course, we are reading all of these videos from the file system, and that requires a really fat pipe as well. So this is a pretty incredible supercomputer. So this is a GPU cluster. Next up, we're really hoping that we're currently working on Project Dojo, which will take this to next level, but I'm not ready to sort of reveal any more details about that at this point. What I would like to do is I would like to just briefly plug the supercomputing team. They've been growing a lot. And so if high performance computing for this application and for training these crazy neural networks excites you, then we would definitely appreciate more help. So please contact the supercomputing team at supercomputing at Tesla to help us build these clusters.